Good morning. My name is Mudawat Lakshman and I'm from CSC F section. Today I'm going to discuss about virtual memory simulator with page fault detection. So, introduction. Virtual memory is a memory management technique that allows an operating system to use more memory than what is physically available. It extends physical memory onto disk storage and provides each process with the illusion of having its own continuous block of memory. The concept ensures efficient memory utilization and enables multitasking by swapping pages between main memory and the secondary storage as required. So, virtual memory is a core concept in operating system that allows execution of programs larger than the actual physical memory. It achieves this by temporarily transferring data from the main memory to the secondary storage. Each process is given an illusion of having its own dedicated memory space. This mechanism ensures efficient memory utilization, multitasking, and system stability. Pages of data are swapped in and out as needed, provided a seamless execution environment even under limited memory conditions. So this is the introduction of the virtual memory simulator with page fault detection. So we are going to discuss and deep diving into this topic now. So what is the need of virtual memory? So need for virtual memory. Physical memory is limited and costly, so that we can use the virtual memory. Large applications need more memory space than available RAM. Virtual memory allows execution of programs larger than physical memory, improves CPU utilization and system responsiveness, supports multi-programming and process isolation. So modern applications often require more memory than what is physically available in RAM. Virtual memory bridges this gap by extending RAM with disk storage, thereby supporting large scale and complex process. It allows multiple programs to run simultaneously without interference and maintenance process isolation for safety. Moreover, virtual memory enhances CPU utilization because a processor can continue executing another process while waiting for another data to be fetched. This makes it essential for modern operating systems and multitasking environments. So now we are going to know about what is the project overview. So this project simulates how an operating system handles virtual memory and detects page faults. The simulator models how pages are loaded, replaced, and how faults occur when a required page is not present in a physical memory. It also demonstrates the working of page replacement algorithms like FIFO, first in first out, and LRU, least recently used, helping the visualize the process of efficient memory management. So here the project simulates the internal working of a operating system's memory manager by modeling sorry by modeling page loading, replacement, and fault detection. When a process requests data that is not in the memory, a page fault occur. The simulator then applies page replacement algorithm like FIFO, and just we now discussed what is FIFO and LRU to decide which memory page to replace. The purpose of simulation is to help the students visualize how virtual memory functions and how page replacement decisions affect system performance. So next we are going to discuss about the objectives. What are the objectives of these virtual memory by the page fault? To understand the concept of virtual memory and paging, to simulate the process of page loading and replacement, to implement the FIFO and LRU page replacement algorithms, to detect and count page faults accurately, to analyze performance through page fault rates. So these are the objectives, like to understand virtual memory and its importance in the OS design, simulate paging and page replacement, implementing FIFO, LRU algorithms to detect count and page faults, to detect and count the page faults dynamically during the execution, to analyze the performance of memory systems by calculating page faults rates and identifying the efficiency difference between the algorithm. So next, what is a system architecture? Input layer accepts page reference string and frame size. Processing layer simulates page replacement algorithm. Memory layer that stores active pages in the memory. And the output layer, it displays the page hits, faults, and statistics. So this is the system architecture, how the system and the simulator follows a layered architecture. Like input layer accepts the user input, the page reference, string, and the frame size, and all those things. Processing layer, it executes the FIFO and LRU algorithms. Just now we discussed simulate the page replacement algorithm. Memory layer, it stores currently loaded pages and manages replacement. Output layer displays results such as total page faults, page hit ratio, and algorithm efficiency. This architecture promotes modularity and helps in extending the project for more algorithm or visualization in the future. So working principle, how it works, how the visualization is works, and everything. The simulator accepts the sequence of page request and a fixed number of frames. It checks whether each page exists in the memory. If not, a page fault occur and replacement algorithm decides which page to remove. The system then loads the required page into memory, updates the count of page faults, and displays the final statistics of the memory performance. So what is a working principle? The simulator takes a sequence of page references and fixes a number of memory frames. For each reference, it checks whether the page exists in the memory. If it doesn't, a page fault is triggered, and depending on the algorithm chosen, the system decides which existing page to replace. The replaced page is written back to memory and a new one is loaded. The simulator continues this process and maintains counter for page fault and hits, eventually providing a clear performance and summary. Next, we are going to know about what is a mathematical formulation to calculate the page fault rate. So let me think, let's say n is a number of page references, and f number of frame available, and page fault occurs if page of I is not belongs to the frames, right? And page fault rate, we can calculate the PFR. We can say that PFR is number of page faults by total number of page references. So here a mathematical foundation of this project can be summarized as follows. Which one? That n is the number of page references and f number of available frames. Page fault occurs when the requested page is not in the memory. It means it's when it is not in the frames. So we can calculate it by the formula number of page faults and by total number of page references. The main objective of page replacement algorithm is to minimize the PFR. So we have to minimize the PFR, which is page fault rate, thus ensuring faster memory and access higher efficiency. For example, consider a page reference string. Here there is a page reference string that are 7, 0, 1, 2, 0, or whatever, like the things. Okay, initially all frames are empty, so the first few results in faults. As new pages are added, older ones are replaced based on FIFO and LRU policy. At the end, the system count 8 page faults and out of 10 references, giving a page fault ratio of 0.8. The simulation shows how changing the frames size and algorithm can significantly affect performance outcomes. So now we go into the code snippet, how this works exactly. So here we are looking at the code. So here is the conditional statements, that is frames dot contains of page. If there is no frames, or like contains, if there is no page, then the page fault should be increased. Okay, if the frame size is equal to the frame size, frame dot size, like what is the frame size here, it might be something else. If both are same, then we have to remove the frame start remove of 0, like we have to remove one frame, or else we are going to add frames, one of the pages to the frame. So the logic ensures that when memory is full, the oldest loaded page is replaced first. The snippet demonstrates that the core of FIFO paging, right, where order of arrival determines the page replacement. Now we go with the advantages of this virtual memory. Efficient demonstrate of OS memory management, helps visualize paging and page replacement concepts, enhances understanding of page fault behavior, useful for educational and research purposes, can be extended to simulate other algorithms like optimal. So here the project demonstrates several real world advantages. What are they? It visually explains how OS memory management works, helps students grasp paging, swapping, and replacement mechanisms, illustrate the impact of algorithm on system efficiency, useful for academics demonstration and research in performance analysis, can be extended to simulate more advanced algorithms like optimal or clock for deeper understanding. So now we go to the future scope. What is the future scope of this project. Integrate GUI for visual simulation, implement additional algorithms like optimal and clock, display real-time memory utilization graphs, add support for user-defined references sequences, compare algorithm performances dynamically. So like we can, as we said, in the future the simulator can be enhanced with a graphical interface to visualize memory frames and page movements in a real time. It can include more algorithms such as optimal, LFU, and clock. Real-time graphs showing page fault rate changes can make analysis more interactive. Additionally, integrating support for user-defined references sequences and comparing multiple algorithms simultaneously will make an advanced educational tool, right? And now we go into the conclusion of this project. The virtual memory simulator with page fault detection provides a clear understanding of how operating systems manage memory efficiently. By simulating page replacement algorithms, it demonstrated the occurrence and handling of page fault in a simple, educational way. The project bridges the gap between theoretical knowledge and practical implementation, highlighting the importance of memory management strategies in the real world system. So, here the virtual memory simulator with a page fault detection provides a simplified yet powerful visualization of how operating system handles memory efficiently. It bridges theoretical knowledge with hands-on application, helping learners clearly understanding page replacement policies and their impact on their performances. So the project successfully shows that by using the right algorithm, memory can be managed dynamically and effectively, reducing page faults and improving CPU utilization. So the references that I covered or I taken from Silberschatz, Galvin, and Gagne operating system concepts. So those are authors. William Stallings, operating systems, internal and design principles. Geeks for Geeks, tutorials point, Java T point. That I taken FIFO and LRU algorithm examples from tutorials point. I taken virtual memory and paging. Geeks for Geeks is like page replacement algorithms and these things. So this is all about the visualization of the page fault. Thank you so much.